Every year, about 4 million people visit Yellowstone National Park to watch Old Faithful erupt on schedule, photograph the prismatic colors of the hot springs, and have lunch in the park cafeteria. Yellowstone is one of the most popular tourist destinations in the United States. It is also one of the most covered geological stories in all of science journalism every few years. A wave of articles appears warning that the Yellowstone supervolcano is overdue for a catastrophic eruption, followed shortly after by a wave of official reassurances that scientists say there is nothing to worry about. Both of those stories are wrong about almost everything that matters. The first story is wrong because overdue is not a concept that applies to supervolcanic eruption cycles, and because the specific claim that Yellowstone is on any predictable schedule has no support in the geological record. The second story is wrong because nothing to worry about is an extraordinary statement to make about a geological system that sits above one of the largest magmatic bodies on Earth, deforms the ground by centimeters per year, drives over 10,000 hydrothermal features, and has in geological terms recently produced 3 of the largest volcanic eruptions in the history of North America. The most interesting story about Yellowstone is neither the one that says it will destroy everything, nor the one that says stop worrying. It is the one that asks, what exactly is it? What has it actually done? And what does that actually mean for the people living near and downstream from it? Yellowstone is a volcanic caldera, not a conventional volcanic mountain, like Mount St. Helens or Krakatoa, but a vast depression formed when an enormous magma chamber empties so catastrophically and rapidly that the overlying ground collapses into the void. The current Yellowstone caldera, roughly 55 by 72 kilometers in size, is large enough that most visitors to the park never realize they're standing inside it. The volcanic system beneath Yellowstone is fed by a mantle hotspot, a plume of anomalously hot material rising from deep within the Earth's mantle that has been burning through the North American plate as the plate drifts slowly southwest over it, leaving a track of ancient volcanic fields stretching from eastern Oregon and Idaho to the current position of the park in northwestern Wyoming. The hotspot itself doesn't move. The continent does, sliding approximately 2 to 3 centimeters per year over the fixed plume, which is why successive eruptions have left a chain of progressively older calderas stretching from the current park location back toward the Snake River Plain. There have been 3 major caldera-forming eruptions at Yellowstone in the past 2.1 million years, the Huckleberry Ridge eruption approximately 2.1 million years ago, the Mesa Falls eruption approximately 1.3 million years ago, and the Lava Creek eruption approximately 640,000 years ago, which formed the current caldera. Each of these was what geologists classify as a supereruption, a volcanic event producing at least 1,000 cubic kilometers of erupted material, a threshold that places each Yellowstone event in a category of geological violence with no modern equivalent in the entire span of recorded human history. In this video, we'll cover 3 things: what those supereruptions actually produced, and what a similar event would mean in concrete terms for the North American continent today, what Yellowstone actually is right now, and what the current hydrothermal system tells us about the hazard the park presents in the near term. In the probability question, what the geological record actually says about the likelihood of another Yellowstone supereruption, and how that probability should inform how seriously we take this particular class of hazard. To understand Yellowstone's hazard profile, both the immediate, ongoing hazard, and the catastrophic potential, you need to understand the structure of what sits beneath the park, which has been progressively revealed by seismological imaging over the past several decades. The Yellowstone magmatic system consists, at its most basic, of 2 connected magma reservoirs. The shallower reservoir, situated roughly 8 to 16 kilometers below the surface, has been mapped by seismic tomography as a body approximately 90 kilometers long and 40 kilometers wide, an enormous accumulation of partially molten rock sitting directly beneath the caldera floor. A deeper, larger reservoir sits roughly 20 to 50 kilometers below the surface and is estimated to be substantially larger still, representing the primary accumulation zone for material rising from the mantle hotspot below. The critical detail about Yellowstone's current magmatic state, and the detail most often misrepresented in popular accounts of Yellowstone's eruption, Risk is the fraction of this reservoir that is actually molten at any given time. Magma bodies are not tanks of liquid rock waiting to be released. They are complex, three-dimensional mixtures of solid, partially molten, and fully molten material, with the melt fraction, the percentage of the total volume that is liquid, governing how eruption-capable the system is at any moment. Current estimates for the melt fraction in Yellowstone's shallow reservoir place it at approximately 5 to 15%, meaning that 85 to 95% of the material in the reservoir is solid or only partially molten, with fully liquid magma comprising a minority of the total volume. This is characteristic of a geologically active but not immediately eruptible magmatic system. For comparison, melt fractions in actively erupting volcanic systems typically approach or exceed 50%. Yellowstone's current melt fraction is consistent with a system that has the potential for future eruption, but is not in an immediately pre-eruptive state by any current scientific assessment. The hydrothermal system above the magmatic reservoir is where Yellowstone's ongoing, present-tense hazard resides. Heat from the magma chamber below drives an extraordinarily active hydrothermal circulation, groundwater percolating down through fractures in the rock heats when it approaches the shallow magma body, rises back toward the surface under pressure, and exits through the park's approximately 10,000 hydrothermal features: geysers, hot springs, mud pots, and fumaroles, which collectively represent the largest concentration of geothermal activity anywhere on Earth. Yellowstone also experiences an extraordinary volume of seismic activity entirely consistent with its thermally and mechanically active subsurface. The park records between 1,500 and 2,500 earthquakes per year in typical years, occasionally punctuated by swarms of hundreds or thousands of small earthquakes within days or weeks, driven by the movement of hydrothermal fluids and the thermal stress on the rocks surrounding the magma system. These swarms, which frequently generate media coverage suggesting imminent eruption, are in fact a normal feature of an active volcanic hydrothermal system and are not, under current scientific interpretation, indicative of approaching eruptive activity, though they are monitored precisely because a change in the character, depth, or location of seismicity could, in principle, signal a change in the magmatic system state. The distinction between seismicity consistent with normal volcanic system behavior and seismicity indicating approach to eruption is one of the most technically demanding judgments the Yellowstone Volcano Observatory is tasked with making. Because the monitoring record for Yellowstone's current active phase is not long enough to establish with statistical confidence what seismic patterns would be genuinely abnormal relative to baseline. This hydrothermal system is not a benign tourist attraction with no hazard beyond the immediate physical danger of the hot water itself, though. That danger is real. And the Park Service documents a persistent pattern of injuries and fatalities from visitors who leave boardwalks and step into or fall into boiling hot springs, which can reach temperatures above 90 degrees Celsius and in several areas higher. The broader hazard from the hydrothermal system involves two mechanisms that operate at much larger scales. The first is hydrothermal explosions, sudden, violent releases of steam and boiling water when the pressure containing a superheated fluid system is suddenly reduced or when the system is destabilized by ground movement. Yellowstone has a documented history of hydrothermal explosions, some of which have been substantial. The Mary Bay explosion crater, now underwater in Yellowstone Lake, has been dated to approximately 13,800 years ago and represents an explosion that would, if it occurred today in a populated area, be catastrophic on a regional scale. Smaller hydrothermal explosions have occurred within the historical record: the 1989 disturbance at Norris Geyser Basin and the formation of new hydrothermal features in several areas of the park during periods of elevated seismicity, illustrate that the hydrothermal system is capable of sudden, significant changes without any magmatic eruption occurring. The second large-scale hydrothermal mechanism is more gradual, but potentially more consequential over longer time frames: the release of volcanic gases, primarily carbon dioxide and hydrogen sulfide, from hydrothermal vents in diffuse soil degassing across the park. Yellowstone is estimated to release approximately 45,000 metric tons of carbon dioxide per day through its hydrothermal system, a continuous volcanic gas output that represents the hazard profile of a continuously degassing volcanic system. not a dormant one. In low-lying areas where gas can accumulate, particularly during still weather conditions, these emissions have produced documented animal mortality events and represent a measurable ongoing hazard for wildlife and potentially for humans in enclosed or low-lying terrain. The geological record of what Yellowstone supereruptions have actually produced is, by any measure, extraordinary, and the scale of that record is important context for understanding what a future supereruption would mean. The Lava Creek supereruption, which occurred approximately 640,000 years ago and formed the current caldera, ejected approximately 1,000 cubic kilometers of volcanic material. To calibrate that number, the 1980 eruption of Mount St. Helens, which killed 57 people, devastated the surrounding landscape and disrupted aviation across the northwestern United States, ejected approximately 0.4 cubic kilometers of material. The Lava Creek eruption was roughly 2,500 times larger. The ash deposits from the Lava Creek eruption are preserved in the geological record across most of the continental United States and have been found in ocean sediment cores off both the Atlantic and Pacific coasts. The thickness of preserved ash deposits varies from meters close to the source in Wyoming and Idaho to centimeters across the Great Plains and Midwest. But the geographic footprint in ash blanket covering a substantial fraction of the North American continent illustrates a basic feature of supereruptions that distinguishes them from every other volcanic event type. Their primary hazard is not lava or pyroclastic flows, but ashfall, which at depths of even a few centimeters collapses roofs, clogs air filters, destroys agriculture, and contaminates water supplies across areas far too vast for any conceivable evacuation or mitigation effort. The older Huckleberry Ridge eruption, dated to approximately 2.1 million years ago, was even larger, estimated at approximately 2,500 cubic kilometers, making it, by volume, the largest eruption known to have occurred in North America in the past several million years. The Mesa Falls eruption, the smallest of the three, produced approximately 280 cubic kilometers, still several hundred times larger than Mount St. Helens. A specific detail from the Lava Creek ash record that bears directly on how we should understand a modern equivalent deserves more attention than it typically receives. Volcanic ash from a supereruption is not the soft, fluffy material the word ash might suggest. It is fine, angular, abrasive particles of pulverized rock, glass, and minerals harder than human tissue, abrasive to mechanical equipment, and chemically active in water. At accumulation depths of even a few centimeters, volcanic ash is heavy enough to collapse structures not designed to bear it, fine enough to penetrate air filters and engines, toxic enough in suspension to cause severe respiratory damage, and acidic enough when mixed with water to contaminate surface water supplies. The Lava Creek event deposited measurable ash more than 1 centimeter thick in some areas across much of the Great Plains, an agricultural zone that didn't exist as such in 640,000 BCE, but that today produces a substantial fraction of North America's grain supply. What 1 centimeter of ash does to a wheat field in Kansas during growing season, at scale across several 100,000 square kilometers, represents an agricultural disruption that current food system modeling has not fully quantified, but that structural analyses suggest could affect global grain markets for multiple successive years. The current monitoring evidence from Yellowstone is extensive and reflects a research investment proportional to the hazard scale. The Yellowstone Volcano Observatory, a collaboration among the USGS University of Utah and National Park Service, operates a comprehensive monitoring network, including GPS and satellite interferometry for ground deformation, seismograph networks, gas emission monitoring, and continuous hydrothermal surveillance. This monitoring has documented several features of Yellowstone's current behavior that are relevant to hazard assessment. Ground deformation at Yellowstone is measurable and ongoing. The caldera floor has experienced both uplift and subsidence in recent decades, with periods of uplift of several centimeters per year, followed by periods of relative quiet, driven by changes in magmatic and hydrothermal system pressures. This deformation is scientifically monitored as a diagnostic signal of system behavior, but it is not at current rates and character interpreted by Yellowstone Observatory scientists as indicative of an approaching eruption. It is, however, direct evidence that the system beneath the park is thermally and mechanically active in ways that distinguish it from a genuinely dormant volcanic field. Yellowstone is not a dormant volcano. It is an active volcanic system in a current phase of relative quiescence. Here is the detail about Yellowstone that both of the dominant media narratives consistently fail to communicate, and that changes the entire frame through which the risk should be understood. The debate between Yellowstone is about to explode and scientists say there's nothing to worry about is a false binary. And it is false in a specific way. Both sides are arguing about the future. While the most important and accurate thing to say about Yellowstone is about the present, Yellowstone is not a dormant supervolcano that might one day become active. Yellowstone is already one of the most geologically active volcanic systems on Earth. Right now, producing measurable ground deformation, continuous volcanic gas emission, thousands of earthquakes per year, and 10,000 hydrothermal features driven by a magma body that has not significantly cooled in over 600,000 years. The distinction matters enormously for how we should think about the risk profile. If Yellowstone were a dormant system between eruption cycles, the only relevant hazard would be the next supereruption. And assessing that hazard would be primarily a question of when the next eruption might occur. But because Yellowstone is a continuously active volcanic system, it carries a spectrum of hazards that exists independently of whether a supereruption ever occurs again. Hazards that range from the immediate and personal, the hot spring fatality pattern, to the regional and potentially sudden a significant hydrothermal explosion of the Mary Bay scale. The probability math on supereruptions reinforces this reframing. Yellowstone has experienced 3 caldera-forming supereruptions in 2.1 million years, an average interval of roughly 700,000 years between events. The last eruption was 640,000 years ago. This timing is often reported as meaning Yellowstone is overdue for an eruption, which is a misapplication of how geological probability works. The average interval between events in a statistically random process does not create an expectation that an event is due simply because the last interval has exceeded the average. By the same logic, a coin that has come up heads 5 times in a row is not overdue for tails. Each flip is independent of the previous ones. What the 3-eruption geological record actually tells us is approximately this: the probability that a Yellowstone supereruption occurs in any given century. If the historical average interval is used as the basis for a random process model, is roughly 1 in 7,000 per century. That is low, approximately the same order of magnitude as the annual probability of being struck by lightning in the United States, multiplied by a large population. It is not zero, and it is not negligible when the consequence of the event would be, as the evidence section established, a catastrophic ash deposition event across much of North America. The relevant question is not whether Yellowstone is overdue, but whether a roughly 1 in 7,000 per century probability of a civilization-scale geological event constitutes a hazard that deserves proportional attention and monitoring, and the answer to that question is clearly yes, independent of any particular claimed timeline. The scale of what a Yellowstone supereruption comparable to the Lava Creek event would actually produce is one of the most studied problems in geological hazard assessment, and the results of those studies deserve to be communicated without either the alarmism of the destroying everything narrative or the false reassurance of the nothing to worry about framing. The primary impact mechanism for a Yellowstone supereruption would be ashfall, not lava or pyroclastic flows, which would be largely confined to the region immediately surrounding the park. Ash from a Lava Creek scale event would be deposited across most of the continental United States and southern Canada, with accumulation depths that vary enormously with distance from the source. Within a radius of approximately 500 kilometers from the caldera encompassing Wyoming, Idaho, Montana, large parts of Colorado and Utah, and portions of neighboring states, ash accumulation would likely range from tens of centimeters to potentially meters in some areas, depending on wind patterns during the eruption. At these depths, ash fall is physically devastating. Roofs collapse under the weight, transportation infrastructure fails, all agriculture is destroyed for the duration of the ash. Water systems are contaminated, and air quality becomes immediately hazardous without respiratory protection. The population within 500 kilometers of Yellowstone is in the millions, and the prospect of evacuating a region that size within the days to weeks of warning that current monitoring might provide represents one of the most challenging emergency management scenarios imaginable. Beyond the immediate impact zone, the agricultural disruption from even 1 to 2 centimeters of ash across the Great Plains and Midwest, the agricultural heartland of North America, which produces a substantial fraction of the world's wheat, corn, and soybean supply, would be catastrophic for food production in the affected region for at least one growing season and potentially longer, depending on whether the ash is removable and whether soils recover or remain compromised. A volcanic winter effect from the stratospheric aerosol injection accompanying a supereruption comparable in mechanism to the Laki and Tambora events this series has covered, but at a substantially larger scale, would further extend agricultural disruption globally for years following the eruption. The global climate impact of a Yellowstone supereruption would, by most modeling estimates, represent a volcanic forcing substantially larger than any event in the historical record, larger than Tambora, larger than Laki, larger than the clustering of eruptions that contributed to cooling in the 536 CE mystery fog event. The specific climate impact would depend on how much sulfur dioxide the eruption injected into the stratosphere, which varies with eruption style and magnitude. But the range of published estimates generally indicates cooling of multiple degrees Celsius globally for periods of 1 to several years following a maximum scale eruption. Against this background, what does current monitoring and hazard preparation actually provide? The Yellowstone Volcano Observatory's monitoring network is specifically designed to detect the precursory signals changes in seismicity patterns, accelerating ground deformation, changes in hydrothermal system chemistry and behavior, and increased volcanic gas emission that geological evidence from other supereruptions suggests would precede a caldera-forming event by months to years. The consensus view among Yellowstone Observatory scientists is that a supereruption at Yellowstone would not occur without observable precursory activity detectable by current monitoring, providing at minimum weeks and likely months of warning, enough time for evacuations within the most immediately affected zones. Though the logistical reality of evacuating millions of people from the western United States is itself an enormous challenge that has received increasing attention in emergency management planning. What current monitoring cannot provide is advance warning of a hydrothermal explosion of the Mary Bay scale, which could occur with little or no precursory activity detectable at the monitoring resolution currently available, and which represents a regional scale hazard potentially affecting the park and surrounding areas with explosive energy and debris that is in some respects more operationally relevant than the supereruption scenario, precisely because it could occur at any time without requiring the magmatic system to transition to a full eruptive state. The infrastructure interdependency dimension of a large Yellowstone event deserves specific mention because it illustrates a feature of the hazard that pure geological analysis often undersells. The western United States contains critical national infrastructure whose disruption would compound a Yellowstone eruption's direct effects well beyond the immediate ash zone: transcontinental electrical transmission lines, fiber optic communication infrastructure, interstate highway corridors, and major rail freight lines all run through the high-impact ash zone from a supereruption, a scope of planning challenge that is without precedent in conventional natural disaster response frameworks. The monitoring also cannot, by definition, change the underlying probability of a supereruption. What it provides is the ability to recognize an eruption in progress early enough to act, not the ability to prevent it or to meaningfully reduce its consequences once it has begun. 4 million tourists visit Yellowstone every year. They photograph bison and watch geysers and eat lunch over a magma body large enough to have buried most of North America in ash within recorded geological memory. And most of them leave understanding essentially none of that, not because the information isn't available, but because the Yellowstone media cycle alternates between sensationalism and dismissal without ever landing in the place where the actual, honest, scientifically grounded conversation about the system needs to happen. Here is what that conversation looks like, stripped of both the alarmism and the false reassurance. Yellowstone is one of the most geologically active volcanic systems on Earth right now, And it will remain so regardless of whether it ever produces another supereruption in a human timescale. Its hydrothermal hazards are real, ongoing, and occasionally lethal. Its probability of a supereruption in any given human lifetime is low, genuinely low. Not we're minimizing it for public reassurance low. And if that supereruption were to occur, it would be among the most consequential single geological events in the history of human civilization. Here's what I want to leave you with. The right relationship with a hazard like Yellowstone is not fear, and it is not dismissal. It is accurate probability assessment maintained continuously and updated as new monitoring data arrives, the same relationship any rational person has with any low probability, high consequence risk in their life. You don't live every moment in terror of the small probability that your house catches fire. You also don't ignore that probability or refuse to install smoke detectors. What you do is maintain proportional, ongoing attention to the risk in a way that makes the response possible if the event occurs, without letting the possibility of an unlikely event dominate choices that should be governed by more probable considerations. Yellowstone deserves that same rational relationship maintained by the monitoring systems currently operating, the emergency management planning currently underway, and the geological science actively working to understand a system that will, at some point in the future, that may be well beyond any human generation alive today, do what it has done 3 times before.